So today we want to talk about linear approximation of functions. Also, we think of local linearity. This is also going to be tangent line approximations of functions. And the idea is this. The best linear approximation of a function near a point is the tangent line. The best linear approximation of a function near a point is the tangent line. So we have some function near a point. So this is the big idea. The best linear approximation of a function near a point is the tangent line. Let's talk about why the tangent line is our best linear approximation. We're going to do this not by thinking about the function. We're going to do this by thinking about the line. What is in a line? A line has two things, depending on how we're thinking about lines, 2 or 3 things, maybe even 4. But a line has two things in this line of thinking. We want to think about a line being made up of two things, a location and a direction. Those are the two things that we need to describe a line. Start here, go that way. Location and direction, two things, location and direction. A line is two things, location and direction. A line contains two things, or a line is made up of two things, a location and a direction, a point and a slope. A line needs two things. What we are going to do with a tangent line is make a line that agrees with the function in location and direction. Everything that a line could possibly agree with a function on. The tangent line agrees with the function in location and direction. The tangent line agrees with the function in location and direction. It goes to the same point and has the same slope. That's everything that a line has to offer. Two things: location, direction, point, and slope. If we make a line that agrees with the function in those two things, that's as much as a line can agree with a function on. We got a point. Oh, I called this x naught. So we get this point, x naught, y naught, and we get a slope. At this point in our calculus careers, we're really good at finding derivatives. At least we're going to pretend that we're really good at finding derivatives. It's not a quiz on finding derivatives today, so you can just agree that you're really good at finding derivatives, right? Y'all are awesome at finding derivatives. You know, I call chain rule, crushed it. Product rule, crushed it. Quotient rule, we know we don't need it because we're so good at the other two. But we know that the slope of our tangent line is going to be the derivative of the function evaluated at the point. The x naught part of the point, that has to be given to us. I have to tell you where I want you to look. To get the y naught part of the point, you just plug it into the function. To get the direction part, you find the derivative and plug in the given point. So the x naught is given. The x naught part of the point is given. I got to tell you where to look. The y naught part of the point we get from the function. So y naught will just be f at x naught. The slope we get from the derivative. Location and direction. So I might say something like this: find the equation of the line tangent f of x equals x squared near x equals 3. So the x equals 3, I have to tell you where to look. So this is our x naught. When I say this is me saying x naught is 3. I need the rest of the location, and then I need a direction, because I only need 2 things to draw a line: a location and a direction. Y naught we get from by plugging our x naught into the function. So y naught is x naught squared. 3 squared, 9. The slope we get from the derivative. So I have my function y equal f of x equals x squared. F prime of x is 2x. So our slope is f prime at x naught, or 2 times x naught. Now I have all the parts we need: a location, 3, 9, and a direction, 6. So y equals y naught plus m times x minus x naught Oops, here's where I find out I didn't open Desmos. I didn't have my graphing calculator ready to go. So there's the point 3, 9. That point is on both of our functions. If I plug in 3 to x squared, 3 squared is 9. If I plug 3 into the linear equation, 3 minus 3 is 0, times 6 is 0, plus 9 is 9. So they agree in location. They also agree in direction. The slope of the tangent line is 6, and that's the slope of the line. So the line agrees with the function in everything that a line can agree on: location, direction. Any questions? Now notice that there's a limitation here. This line is a very good approximation if we are standing close to the point 3. Here we are at 3. Oh, it's not going to let me log on. See, the problem is it's tangent, so it doesn't cross, so Desmos won't like lock the point on. But the further we get from 3, the worse the approximation gets. Notice that when I try to plug in 4, the line at 4 is 15, but 4 squared is 16. The further we get from 3, the worse this approximation works. The worse this approximation is. That's why we refer to this as local linearity. It's going through the same point and going in the same direction, but it's also not changing direction in the same way as the function. The further we get from 3, the worse our approximation gets. When x is 0, x squared is 0, and our line is down here at -9. So that's a very bad approximation. I've tried this one on like the IRS. They're like, oh, Mr. Leach, you owe us $9. I'm like, oh, that is approximately 0. And it worked for about a minute. It's like, oh, trust me, I'm a professional mathematician. And I'm like, oh, well, he's professional. No, we're not going to fall for that. We know you're a teacher and therefore don't have any money. I'm just kidding. They just say we shouldn't drive our Ferraris to school. It's ostentatious for all the teachers. So just keep it in the garage and drive by. I'm just kidding. I don't have a Ferrari. I have taste. I'm just kidding. I don't have any taste at all. I have a Lamborghini. Just kidding. My mechanic has a Lamborghini. Just kidding. All right, so the idea is that this is local linearity. This is a good approximation so long as we're near x equals 3. The further we go from x equals 3, the worse our approximation is going to be. Farther we are from x equals 3, the worse our approximation is going to be. Because all we're matching is location and direction. And the function x squared is doing lots of different changes in its direction at all kinds of different points. The line is just giving you one direction. Any questions? Yes. It's bad anywhere other than that point, but it's good near that point. And it's weird to approximate a function as simple as x squared with a line. That's kind of strange. So if your question is like, well, why would we approximate such a well-known function with a line? The idea is that we wouldn't want to approximate a function, especially with all the phenomenal amounts of computing power we have. We know some weird functions to very great detail because of our computing power. But one of the things that we're going to want to build on is, what if we want a better approximation? Because this is calculus. What do we want a better approximation? A line only has two things, a location and a direction. And that direction never changes. So what if we wanted to build on that? What if we wanted to make a better approximation? I've got a 0-degree term. I've got a 1st-degree term. What would I do to get a better approximation? 2nd-degree term. And what if I wanted a better approximation than that? 3rd-degree term. The point now is that we'll be approximating a function, not just with a point or a line or even a quadratic, but with any degree of polynomial. The reason that polynomials are good is that polynomials only involve multiplication and addition. And those are nice and simple operations. So that's kind of a bigger picture of where this is headed. It's not necessarily about using lines to approximate functions, especially when we have the function in hand already. So great question. Why the heck would we do this? It's a bigger, more than just doing this. So for future, this will lead to higher degree approximations. And the reason that we're happy about this higher degree polynomial approximation business, is that polynomials are very simple objects. They just involve multiplication and addition. They have exponents, but the exponents are all constants, so and integers and non-negative integers. So I mean, dope. So the reason we like this is that polynomials are super simple. They just involve addition and multiplication. So we like polynomials. So if just as a side note, just for pattern recognition purposes, I'm matching the function, the first derivative. If I need a second degree polynomial approximation of a function, what do you think I might be looking at? I got a 0th derivative, a first derivative. What do I need next? A second derivative. If I want a third degree polynomial approximation, what would I need? Third derivative. And we're just going to make those derivatives match the function at the point. Congratulations, you just finished chapter 10 in this book from Calc 2. By the way, next semester when we get to chapter 10, I'm going to be saying, hey, remember finding tangent lines? And you'll be like, oh, yeah, we're just going to keep going. And you'll be like, oh, got it. And you'll be like, I'm matching derivatives. Where did this come from? And you always know. And then one of you will remember, it's like, oh, no, you told us last semester that this is what was going to happen. I'm like, oh, that's because I can see the future. And you're going to be like, oh, no, you can't. It's just that you planned this because you knew you were going to be teaching Calc 2 next semester. So you told us that this is not surprising. Except for the students that are in my Calc 2 class, but not this Calc 1 class. And they're like, oh, wow, how did you guys know that? For them, it'll be like, oh, we're just really good. So remember that. The other idea is that we want to know that we can do this. Part of knowing that we can do this is that this can be done. That's sometimes the biggest question, is not knowing what to do in a particular situation, but figuring out what to do because you know what can be done. Let's suppose I give you like some sparse information. Let's suppose that g of 2 is equal to 7 and g prime of 2 is equal to -5. So without even me asking a question, what are we going to do with this information? What's the thing that we're doing this day in calculus? The thing that we're doing today is finding a linear approximation of a function near a point. And for that, we need the location and a direction. What did I just hand you? A location and a direction. So we're going to make a, I don't even have to ask questions sometimes. I could have a quiz and just do this. And then I go, suppose this is true, do something. Tangent line. And then I go, yes. And then I go, all right, I can, problem writes itself. So we have here a location. I'll just kind of pink and blue. Location. And direction. So without even seeing what the question is, you can be like, oh, y is equal to y naught. That's where y starts. Plus m times x minus x naught. This is our best approximation of whatever this function g is, the best linear approximation. It has the same location and direction as whatever this function g is. We don't know what the function g is. So I can give you a location and direction, then ask you, not tell you what the function is, and I ask you to approximate g of 2.1. What's going to happen shortly after this? It would be ridiculous if I said approximate g of 10. That's too far from where we have this information. We would want some updated information. And also, if we knew what the function g was in the first place, just plug 2.1 into that function. But with this limited amount of information, location, direction, this is the best we can do. So we'll just plug the 2.1 into our line. So I'll do 7 minus 5 times 2.1 minus 2. 2.1 minus 2 is 0.1. G of 2.1 is about 6.5. We're decreasing with a slope of 5. So if our delta x is 0.1, our delta y will be negative 0.5. And so 7 minus 0.5 is 6.5. A delta x of 0.1 leads to a delta y of negative 0.5. So g of 2.1 is approximately 6.5. Question? How's that, brother? At this point, we don't have enough information about the function to decide if this is a good approximation or a bad approximation. We don't know how the rate of change of this function is changing. We don't know how curvy this graph is, or this function is. So we don't have any information on the curviness of the function g. If g is super curvy, this might be a terrible approximation. If g is not that curvy at all, this might be okay. If we had more derivatives, we can make a better polynomial approximation. Moreover, not only will we have a better approximation by having values closer to the true values of the function, but it might work on a wider interval. So by better approximation, we mean a couple of things. It could be closer to the actual value, and our approximation might work on a wider interval, farther away from the point we're interested in. But only maybe a wider interval. These are the two things that we get from what we might call a better approximation. Closer to the actual value, and maybe it will work on a wider interval around that point. Because remember, we're making a local approximation. We're taking a bunch of information about the function at one point and extrapolating from that one point. How's everybody okay? This DVD bonus material. So if they're like, oh no, at limit, too much. Oh, actually, are DVDs still a thing? Maybe this is Blu-ray bonus material. Is physical media still a thing? We used to have these things called Blu-rays, and the movie was on this disc. You have to put this disc into like a player and watch the movie that way, instead of just having it show up on your TV through the internet. The second degree approximation starts off with the tangent line, and then we just add another term. Unsurprisingly, it's a squared term. Surprisingly, that term gets divided by 2. What I've done here is raise a question. First of all, I've confirmed that all we have to do to make a better approximation is add more terms. I actually didn't confirm that, I just stated that. And everybody's going to go ahead and believe me because I'm in the position of authority. I'm going to go, all right, why would we do that? At least you said to do that. But something weird showed up. Tangent line like normal. Why not? Plus m times x minus x naught. But then my squared term has that x minus x naught squared. And then there's the 3 for the second derivative. But then that got divided by 2. And then the third degree term, I got the x minus 2 to the third. And I got the 6 to be the third derivative evaluated at 2, but then I divided that one by 6. That raises a question. Why these denominators? Where do these denominators come from? Now, I could tell you, like right now, where these denominators come from and snap all of this into place all the way to where this actually shows up, which is in chapter 10, where we talk about Taylor polynomials. So that's what we're doing, is we're building a Taylor polynomial. We've been building a Taylor polynomial all day. A linear approximation of tangent line is a first-degree Taylor polynomial. So, but if I really want to make that stick, if I really want you to understand things like instantly, all the way out through chapter 10, just kind of snap all that calculus into place. I can tell you right now where that 2 and the 6 come from. We'll just tell you right now where 2 and 6, but only if I do it right now. If I wait till tomorrow, it's all ruined. The effects will be ruined. So let me tell you where the 2 and the 6 come from. So all this calculus would make sense all the way through chapter 10, and we won't have to do any more work. So the 2 and the 6 come from, dang, look at the time. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.